the purpose of this video, and actually the next couple of videos that we're going to talk about in the next couple of sections, is to talk about various aspects of probability distributions. So along those lines, we need this idea of what we refer to as mathematical expectation. So this goes along with section 2.2 in your text. Let's suppose that you take a regular old six-sided die that's got numbers 1 through 6 on it, and you just decided to roll it, say, 10,000 times, or 100,000 times, or 1,000,000 times, a whole bunch of times. All right, so we're rolling an ordinary die, numbers 1 through 6, and each of the outcomes are equally likely. So if you do this over the long run, you would expect that each of your outcomes, 1 through 6, would appear roughly the same number of times, especially if you roll a die 1,000,000 times, or 1,000,000,000 times, or 10 billion times, whatever. You would expect the same number of 1s as 2s as 3s, and so on. So if you were going to look at the average of all of those rolls, you would expect the average to be roughly 3.5, because again, we expect as many 1s as 2s as 3s and so on, so really you just average up 1 through 6 and take the average of those, so it really should be like 3.5. What if we change the die? What if instead of having an ordinary six-sided die, we change the numbers where there's only one side has a 2 on it, and the other 5 sides have a 5 on it? What happens then? So in the long run, in this particular case, if we've got a die that has 1 2 but 5 5s, we would expect to see 5 times as many 5s show up as 2s, because 5 is certainly 5 times more likely to be rolled than a 2 is. So notice in this particular case that the probability of rolling a 2 is 1/6, and the probability of rolling a 5 is 5/6. So if we want to average out the rolls now, again, we would expect 5 times as many 5s as 2s, so we would need to average the numbers 2 and then a 5 5s, and then we would get the average of the roll is roughly 4.5 instead of 3.5, which we would expect. We got a lot more 5s than we do with 2s, so the average should be closer to 5. Okay, so we could have also done this computed the average, looking at it as a weighted average. So I mentioned, notice that the probability of a 2 was 1/6, and the probability of a 5 was 5/6. So that means that a 2 should show up 16% of the time, 16.6 repeating percent of the time, and a 5 should show up 5/6 of the time, 83.3 repeating percent of the time. So we can use those probabilities of weights to figure out the average. In other words, what we could do is we could take the 2 times the 1/6 plus the 5 times the 5/6 to get 27/6 as well. So that leads us to our definition of expected value of x. So start with a random variable, has a support s and a PMF of f of x. Then the expected value of x is this weighted average idea. I'm going to take each x in the support, I'm going to weight it using the probability function. The probability mass function is why we use the name probability mass function. If you've done any physics and done some weighting of point masses, it's the same idea. It's through that idea of weighted average. So we're going to take the value times the probability and add those up, and that'll give us the expected value. We don't have to do it just for x. We can do any function of x. So if we have a u of x, then we can multiply the PMF by the u, plugging in each value over the support. So let's do a couple of these. All right, so this looks familiar from the previous video. This is probability mass function of x over 10 for x equals 1, 2, 3, 4. Let's look at expected value. We take x times the PMF, so x times x over 10, and we're going to plug in the numbers 1 through 4 because that's the support, and we're going to add it up. So just this little simplifying here, x times x is x squared. We plug in 1, plug in 2, plug in 3, plug in 4, and then add those things up, and we get 3. So the expected value is 3 in this case. So what that would mean is if we ran this random experiment over and over and over and over again with these probabilities in the long, and then looked at the outcomes, 1, 2, 3, or 4, if we did the average of those over the long run, we should see an average of about 3. Theoretically, if we did it infinitely many times, we'd get exactly 3. But if we did it a finite number of times, we should get something that's really, really close to 3, as long as the x is large, or the number of experiments is large, sorry. We said we could do any function of x, so let's say instead of just an x, we had an x squared. In this case, then, we would multiply the PMF by x squared, by whatever this function of x is here. But we're going to do the same thing, plug in the values. So x squared times x is x cubed, and plug in those numbers, and we get 10 in that case. So that would be our expected value of x squared. There are going to be some properties of the expected value that we're going to find useful in the future. So the first one is that the expected value of a constant is just a constant, no matter what that constant is. And that makes sense, right? If you're looking at just getting a constant out every single time, over the long run, if you average it up, you're just going to get that constant. The second one says that if I have a constant times a function, and I look at the expected value, I can pull that constant out in front, and it's the constant times the expected value. And the third one says that the expected value behaves well with linear combinations. And what that means is that if I've got a constant times the first function, plus a constant times the second function, we can break up the expected value over the sum and pull the constants out. So let's look at a proof of these. Here is expected value of a constant. We would take the constant times f of x. This is just a sum. I can pull the constant out of the sum. And now using our probability mass function properties, since we're just summing up the PMF over the entire sample space, we just get 1. So we get C. So that was the proof of the first part. Second part, again, if I have constant times function, I can pull the constant out, and this is the definition of expected value of u of x. So that was pretty straightforward as well. So all I did is just using the property that I can take a constant and factor it out of a sum. It's literally what it is. So if I look at the third part, same idea. Expected value is defined as take the function on the inside and multiply by PMF. In this case, we can distribute the PMF over the sum. And now I've got a sum of a sum. Well, addition is commutative, so I can break up the sum, the summation over that sum. So I can split it into two pieces. And then much like what we just did in the previous part, I can pull the C1 out of the first sum and the C2 out of the second sum. And then I recognize the first expression. This is not correct. This should be C1, expected value of u of x1, or u1 of x, sorry, and this should be C2, expected value of u2 of x. So this is a typo. The C1 should be out in front, so it should just be expected value of u1 of x, close that parenthesis. C2 should be in front of expected value, should be right here, and then expected value of u2 of x. My apologies for the typo. But let's see how we use this last property. Say we want to find this expected value of x squared minus 6x plus 2. Well, using this property here, we can break up the expected value over the sum of the three pieces. This is really just a sum. And using that property 2 we proved, in the second piece, I can pull out the negative 6. So we get expected value of x squared minus 6 expected value of x plus expected value of 2. We already computed expected value of x squared was 10, expected value of x was 3. Those were already computed in the example that we did. And then expected value of a constant is just the constant. That was property 1 we just proved a little bit ago, and we get negative 4. So we'll do more of these in class. I apologize for the typo here, but again, just think of the expected value as in with the u's and the constants have been pulled out.